Good morning, students. Today we are going to start with Diffie-Hellman key exchange algorithm, and I have some of the examples also. And through that examples, we are going to find out how the Diffie-Hellman algorithm is going to work out and how we are going to do in this. Okay, for all the purpose, we are going to find it out. Okay, so now you can see this in this Diffie-Hellman key exchange. We have the example of color mixing example. We will see how we are going to use this color mixing example and how we are going to do. So now why we are using this Diffie-Hellman exchange? Okay, so that is a main thing to find it out why we are using this Diffie-Hellman exchange. So here what we are going to do is, the first thing is it is a method. Okay, first you have to remember the Diffie-Hellman key exchange, it is a method. Okay, where this is going to use, or it is going to utilize, where it can securely exchange the cryptographic keys. Okay, so we are going to exchange the cryptographic keys. So now how we are going to you exchange the cryptographic key, and where we are going to exchange, we have to exchange this cryptographic key over a public channel. Okay, yesterday I have shown you in my last class some of the channels are there where the Alice wants to send the message towards the Bob, but due to the third party, the Alice is not able to send any kind of key or message towards the Bob. So where we are sending this message? By using the public channel. So here what will happen is, when we are sending the like a message from one place to another place, so how securely we can exchange all the message from source to destination. So here we have a new concept, that is Diffie-Hellman key exchange concept, where the Diffie-Hellman will exchange the key, secret key, priorly sending the messages and all. So here another thing is also there. In this concept has been implemented in 1976 by Diffie and the Hellman. Okay, so two scientists, those who have generated this kind of key exchange algorithm. So let's move towards the first slide. Let's see what is happening in this. So here you can see what is the problem is arising in the key exchange. As you can see the slide, the main problem will be there with the symmetric key encryption, which is require a secure and reliable channel for the shared key exchange. Already I told you that whenever we will exchange any kind of message, we have to use the public channel. So that public channel will not be very secure or reliable channel. So if you want to share any kind of public key or symmetric key with your like a destination team, so that time the channel through which you are sending the key, it has to be very secure and it has to be very reliable. So what is happening is, as it is a public channel, anyone can take the key whatever we have been shared. So that is the reason the Diffie-Hellman produces one kind of your protocol through which we can create the confidential shared key, and we can share it over the public channel without informing the third party. Okay, so here this is the concept. Before that, what used to happen is, the secure encrypted communication, whatever happened in between the two parties, they used to require the first you need to exchange the keys, and with some of the physical layers or physical channels, like you can say that like you are trusting someone that you are sending the key through them. Okay, that is your also one kind of your public channel. Through them you are sending the data. But in this Diffie-Hellman key exchange, priorly without the prior knowledge about the two parties also, they can share the keys. Okay, so once a shared keys will be the secret key will be shared in between the two parties, then they can encrypt the communication by using this symmetric key cipher. So here you can see that this scheme, as I told you already, this scheme has already published in 1976, and the two scientists' name is Diffie and Hellman. The name of the first scientist is like Whitefield Diffie, and the second person name is Martin Hellman. So in 1976, they have produced this protocol where it's going to give you the public channel through which you can share the confidential key. So moving to the next slide, what is happening actually here? Modular what? It means that here the shared encryption key will be relying on your modular exponential or primitive roots and the discrete logarithm problems. So here we have to concentrate on modular exponentiations. Okay, so modular values we are going to find out, and also along with that we have to find out the primitive roots, and also with that we have to find out some of the discrete logarithmic problems. So these three things has been added inside your Diffie-Hellman exchange algorithm. And also it will not be that much of complex mathematics, but it is very easy to use also. So now you can see here a difficult one-way problem, how the problem arises and how we are going to do it or solve it, the operations. Okay, so here you can see in our like whatever the example we have taken the example of mixing colors. So through this example you will understand how we can share the secret key with the partner and how we are going to send a message by using the secret key. So here what we are going to do is we have to mix two colors, okay, and which is very hard to unmix also. So let's see here. You can see the diagram now. Alice and Bob, and with one more person is there. So what they are going to do, they are going to share the secret color. Okay, so before that we used to have the secret key, where secret key in the sense some data we are transforming. So just to understand in proper manner, I have taken the secret color. Okay, so now A wants to send the data or secret key, or that is known as my color, to B. So what it is happening, you can see now the A is sending yellow color towards B. Okay, so A is saying that the yellow color will be my secret key. But what happened? The third party has hacked or attacked on the public channel, and it came to know about the yellow color, and it has been taken that yellow color. So now if I will share any of the data, I cannot tell you that this is secure, because already the yellow color has been shared. So now how we can apply our Diffie-Hellman key exchange algorithm to prohibit from this kind of attacks? So now next what we will do is, we have to in the step 2 we will pick a secret color. Okay, because we know that our yellow color will be attacked by the attackers. So the A has taken one secret color, that is orange color, and B has taken one more secret color, that is, let's take it as your green color. So now A and B doesn't know that which color they have picked up. In the next case what they are going to do, so they are going to add their secret color to the shared secret color, which has been shared already. The yellow color already has been shared among A and B. So now what you are going to do, they are going to add these two and they are going to get a new color. Okay, so A will have one secret color, that is orange, and that orange color she is going to add with the shared color, that is yellow color, and she is getting this kind of color. Okay, so now what B is also doing, B has already the shared color as yellow, and he has one secret color as green. So he has added both green and yellow, and he got some of the color like this. So what will happen in this case? Now the attacker is very clever. So what he will do is, now he is going to take, because when this A will send her color, the whatever the mixed color, to the B, that time through this public channel, that time the attacker can take her color, right? So the attacker has taken this mixed color here. Fine. While sending this mixed color from A to B, the A to B, it has been reached over here, and also simultaneously the attacker has attacked that value and the color is here also. Similarly, in the same process, the B also sharing his secret color, which one, that is this mixed color, towards A. through the public channel. While sending through the public channel, the attacker has attacked that, and that color also has gone over here. Now the attacker has three variety colors, but he doesn't know that which one has to be used. And A has also two variety colors, B also has two variety colors. So now what is happening from here? Here you can see that the color whatever is there, how it has come. Let me take that. Let me take about A now. Okay, so in this A, what has done, she has added orange with yellow and got this color, right? So now what she is going to do, she knows that we have shared the color as yellow. Okay, so if I will whatever the color has been shared from here, if I will take out the yellow color, whatever color will be remaining over here, that will be the secret color of the B, right? So similarly in B side, the color has been shared, this one, right? This one was A has been shared. So the B, what B will do, B knows that the yellow color has been shared among A and B. So if I will take this yellow color from this, I will get orange color. So that orange color will be the secret key of A. So in this way, they will come to know the secret color of each, but the attacker will not come to know that which color, like if he will also take out, then which one is from which side. He will not come to know that for what color has to be take out, what will be their own secret color. They won't come to know. So same thing has been written over here from Ali's side. Okay, from Ali's side. So here Alice what he has mixed and Bob what he has mixed. So Alice what she has mixed is yellow color and that orange. So that teal color, and from the Bob side and plus orange color. You can see all these things. So from here if I'll take out yellow color, then she will understand that from Bob this teal color has been come out, right? So similarly from Bob whatever mixed color he has, if he will take his own colors out, then he will understand that orange color was the secret color of Alice. So this is the way where the Alice and Bob has been agreed to share their color among themselves without knowing the third party. So here you can see again how is it that Alice and Bob's final mixture is a secret. How we came to know? Because that third party will never know that the knowledge, whatever the secret colors, how they have shared, how it has been shared among your Alice and Bob. So unmixing a color into its component colors will be a hard problem, because there will be two things. One will be your easy problem, one will be your hard problem. So easy problem will be like mix some two of the colors and share it over your public channel. But hard problem will be how to unmix the color, because we don't know which color has to come out and what will be the remaining components. So through that, it will be a hard problem to understand whatever the Alice and Bob has been shared among themselves. So this is a problem happened. So this kind of problem has been solved by using this Diffie-Hellman key exchange algorithm. So now we are going to add the mathematics term into this color, okay? Because we have taken the color example. Now you understood how we are going to take the colors and how we are going to take out the colors. So now if I will add the mathematics into this, how our problem is going to look out. Now let's go back to the math, and now let's see how we are going to solve the problem. I told you one will be easy problem, one will be hard problem. So here in the question paper, you will be having the given values of some values, okay? And you are going to solve some of the values. So here you can see it is a prime number, S is a prime number, and where you are going to find out this, okay? So G value, N value and P value will be given in your question paper to find out the S value. But suppose in the question paper you got S value and G value and P value given, then it will be little hard for you to find out the value of your N. So how to solve that we are going to see now. And one more property will be there as per mathematics, you know, G power A into B, A and B will be nothing but that is my secret key, okay? So whatever the secret key has been shared here, modulo P will be equal to G power B into A. So alternative A into B will be also equals to B into A mod P. So you just remember the property. So whatever the secret key has been shared in one side, that also will be provided in the another side. Only the terminology will be different. So now let's see in our example how we are going to do. So Alice and Bob has publicly agreed that they are going to share the large prime number, which is called as your modulus or P. So which one is your large prime number? My large prime number is P. So you see in this previous slide, S equals to G power n mod P. So P is nothing but it is a large prime value. Okay. So you remember whenever in the question paper it has been given that the large prime number value is this much, you will understand that that is the value of your P. So now next step, Alice and Bob publicly agree to a number called the generator, or you can say it as your G. So which has a primitive root relationship with P. So if in the question paper it has been given that the number shared by Alice and two parties, sometimes it will not written Alice and Bob name, it will be written like two parties. So the number has been shared in between two parties, like your primitive root, the value is this much. So that time you will understand that is the value of your G. Okay. So how to find out the value of your P? It will be given large prime numbers, and if it has been given primitive root, then you have to take the value of G. So now let's assume as some question. So P value has been given 17 and G value has given 3. So now what we are going to do? So these two values has already been, it has been declared, it has been already shared with the third party. So the third party already knows the value of your P and G. So now next step, what you are going to do? Now next case, we have to select the secret key. So in this secret key, how you are going to select? The first thing is the Alice has to select the secret key. So what is the secret key? Let's take the name as A. So now the Bob also has to select the secret key. Let's take the Bob secret key is B. So in the question paper, if it will give that there will be two secret key, 54 and 24, then you will understand that the value of your A will be 54 and the value of your B will be 24. But the secret key, whatever has been shared among your Alice and Bob, the third party will not be knowing about the A and B, because you know how these values has been shared. They will mix it with some other values and they will share it among the among both of them, and that too through your public channel. So the third party will not come to know about the secret key. Now let's move to the how we are going to combine all these things and how we are going to find out the public informations. So now what the Alice will do? Alice will combine her secret key of A with the public information whatever has been given. What is the public information has given? That is the value of your G and P. What is the value of our, according to the example, the value of your G is 3 and the value of your P is 17, which is a public information. But what is the secret key? That is the value of your A. So that is my 54. So these things has been going to be computed in the side of your Alice. So you have to find out A value, and similarly you have to find out Bob value also, that is B value. Okay, so now let's find out the value of A. So in that previously I have shown you that here S. So now you can write A here. So A will be equal to G power A mod P. So what is the known value given already? G, A and P, everything is given in the question paper. So G value is 3, power 54 modulo 17. You have to find out the remainder value. So how much you got? You got 15. So now A has shared the secret key as 15, okay, towards the B. Now let's move towards Bob. So in the Bob side, he will also combine the secret key B and with the public information, and he will compute the value of B. So now how to find out the B value? What is the formula? G power B mod P. So this G, B and P, all the values has been given in the question paper. So the G is 3 power 54 modulo 17. So now you got the value as B value as 16. You can try it out in the calculator and you can find out the remainder value. So once it has been done, now what is the next step? You have to share the combined values. So now the Alice has shared the combined value towards your Bob. What is that value? She has shared A value as 15. And what is the value B has shared? He has given the value as 16. So now this A and B value was a private to your third party and it has been shared among your Alice and Bob. So in this way, you are going to share the values. Suppose if you want to check it out that what is the key, whatever they have shared, because the value we got it, but actually among that, how to compute the shared key. So that is the again formula. This is the inverse formula of whatever we have written. Okay. So now here you can see Alice computes the shared key. So what is the formula? Here I have written G, right? G power of A. So G is nothing but B mod P. Fine. So here also one more formula, as you already know, this one already I have told you that G power B into A mod P also similar to G power A into B mod P. Right? Why I have written B into A? Because I am now inside my Alice, okay, who is going to share the secret key towards the Bob. So the value of B has to be mod of P of A, because A is the secret key of my Alice. So now G power B into A. So this is 3 power 54 into 24 mod 17. So now here you got the value as S equals to 1. So now similarly, if you are going to compute in the Bob side, then how you are going to do? A mod P whole power of A mod P. So now this value of this one is already we discussed, that is G power A into B mod P. So now 3 power 24 into 54 mod 17. So you got the value as S equals to 1. Now you can see the values of A and B are Alice and Bob are same. You can try it out in the calculator. Okay. So now next step will be what is the encryption key which is unknown to the third party. So how we are going to find out? In our previous example, we got the encryption key as S equals to 1, and this key has been shared among your both the parties to encrypt and decrypt the message. So this is the way to find out the encryption and decryption of the message by the both the parties. Okay. So in this way, the Diffie-Hellman key exchange algorithm works out, which you are going to get some around 8 marks with the example to solve it. I hope you have understood this concept. Thank you. Okay, so now I'm going to show you how you are going to find out the reminder values by using the calculator, because if it will be a big number, then it is very difficult to find out because you will be having the exponential number. Okay, so how in shortcut way you can find out quickly by using the calculator. So let's take the example as this is my example. So let's take it as 52 divided by 12, or you can say that 52, I'm going to find out 52 modulo 3 varieties way I am writing so that you can understand. This is a modulo value you can find out. Okay, and also you can write down one more way also, that is 52 modulo. Okay, so 52 modulo 12. So now suppose if I want to find out in normal way, I'll just do it in this side my rough way. How we are going to do in by hand, if you it is a small number we will do, right? So 52 divided by 12. So you know 12 fours are 48. So if I will do it 12 fours are 48. So what is the remainder value I'm going to get? I will get it as 4. So I know that the 4 will be my answer, right? The 4 will be my answer. So now how I'm going to find out? By using the calculator. So the first step is I have to use, the first step is I have to use 52. I have to do 52, okay, divided by normal division divided by 12. So if I'm going to do 52 divided by 12, then how much I'm going to get it? Let me use the calculator here. 1 minute. So if I'm going to do 52 normal division by 12, I'm going to get 4.33. Okay, so I'm going to get here 4.33. You people can try also by using the calculator. 4.33333, some values I'm getting. So now next what you are going to do is, whatever the values you are going to get here, that you are going to minus it with the whole. Okay, so now I'm going to write in the next step. I got the value as 4.33 and 3. I'm going to minus it from the value whatever I got it from here. So how much I got? So 4. So what is the value? If we will subtract both the things, you are going to get 0.33 and 3, right? So now the next step, what you are going to do? You got this value. Next step, we have to multiply. So with whom I'm going to multiply? So with this value, whatever I got, that is your 0.33 and 3, you just multiply with your, how much is the value here? You, whatever the value you have here, that is how much? That is 12, right? So you are going to multiply it with the value of your 12. So here I'm going to multiply with 12. So now I'm going to use a calculator. If you want, you can use your calculator and just check it out the values. So if I'm going to multiply with 0.333, I'm using the calculator, normal calculator, into 12. So I'm getting the value of 3.99. If you will take the value as 0.33, okay, 0.33 into 12, we will get some 3.96 or 3.97, something like that. You are going to get it. Okay, so you can make it as your whole number. Fine. So here I'm going to do, so I will just multiply and I'm getting some values as your 3.9. So here you can make it as your whole number and you can find it out as your 4. Okay, all these things are happening because of your decimal values, and you can round it up as your 4. So this is the way how you're going to find out the values in a normal calculator. Fine. So now, so here I got the values as 4. So now here one more question I will give you to solve also. If possible, you just do it. So I'm just giving you one more question. The question is 1742. Find it out the modulo with 512. Just find it out. That will be easy for you. So as per the answer is coming as 206. So please follow the process and do it accordingly.